Everybody, let's give a warm PyCon welcome to Adam Fletcher and Jonathan Mortensen.
Thank you. All right. A little bit of technical difficulty. Sorry. Let's. All right, great. Our slides. Sorry that they're not completely full screen. That's okay. So hi, I'm Adam Fletcher, and with me is Jonathan Mortensen. Hey. So we ran a company called Gyroscope Software, and we made developer tools powered by AI. And last year, we got an invite to the Samsung Developer Conference, and we weren't really sure what to do about it, right? As a developer tool, we wanted the press, and we wanted the exposure from the conference. But also as a developer tool, our booth was destined to be super boring, right? Like we'd give you a free t-shirt, and maybe you'd watch like a looping video of our software in action, and that's not good. So we look for something more exciting. One thing that is obviously more exciting than a conference booth is blood sport-style underground street fighting. Ideally starring the muscles from Brussels, Jean-Claude Van Damme, seeking revenge for the death of his brother. That is, I think you'll agree, that is clearly more exciting than a conference booth. But we are nerds. And as you can see from our physique, we are not Jean-Claude Van Damme yet. It's coming. So instead, we decided to see if we could train an AI to play Street Fighter II on the SNES, and then run an AI versus AI Final Four style tournament during the conference. And today, we're going to talk about how we used Python to do just that. So first, let's start with the overview of the technologies we use. This is useful. So Super StreetFighter II Turbo runs on the Super Nintendo. But in order to gain the control and speed necessary to do good AI, to train the AI, we couldn't use the actual Nintendo hardware. So we used an emulator called SNES 9X. And then we used an emulator environment that let us program the emulator from afar. This is a tool called BizHawk that the tool-assisted speedrun community builds, right? BizHawk is written in C#, and we had to add some code to that, which we'll talk about in a second. And then we used Python to use Jim, a package from OpenAI, and Jim used some Python agent code that we wrote that uses keras-rl and tensorflow. And so we're just going to dive straight into these elements, and I'll describe the results at the end. And what follows is the story of how it actually happened in terms of code and data science. And so if it's going to seem a little disjointed, that's because we were on a voyage of discovery as well, and that's the nature of the story. First, the Jim package, right? So this makes sense as a starting point. Jim lets us create a representation in Python about what's happening in the game, and lets our agent interact with that representation. We're using a technique called reinforcement learning, and this is kind of the simplified diagram of what reinforcement learning is, right? In reinforcement learning, you have a continuous cycle of reinforcement by having an agent examine the state of an environment, then take an action, then seeing if the reward, the result of that action, is maximized. And we're going to talk more in depth about this, but it's useful to kind of keep this in your head as we go. And the OpenAI Jim project provides the environment portion of this. And in Jim, the environment is what you're doing reinforcement learning on. And OpenAI has actually built a number of good environments for retro gaming, including for the Atari games. And I think they recently had a retro gaming competition that might still be going on. But they did not provide an environment for Street Fighter II. And another big thing that Jim provides is a very clean abstraction that can be used for doing this sort of machine learning, right? And I'll talk about the key elements of this abstraction: the action, the observation, reward, and the two functions, step and reset. And we'll go into each one of these in some detail. First interesting one is the observation. That is the data that represents the world the agent will learn about. And in our case, it's pretty straightforward. It's Street Fighter II, just as a human would see it, right? It's everything a human knows. It's the timer, it's the health bars, it's what your opponent's doing, right? And each environment needs you to define this observation. It Jim gives you tools for doing that. And on the right-hand side is code you don't have to read, you shouldn't care about. It's just basically, look, these are all the things we tracked. This is all the dictionary of all the things we tracked that represent our observation. Right, and there's a few ways to get this. So you can get this in some papers you'll read on this sort of thing. You'll get this from image recognition. People will train image recognizers to see where characters are and where points are. We actually had the advantage of using an environment that gave us direct access to the memory of the game. And so we actually just extracted these values out of memory, but we didn't do anything that a human wouldn't do. So we didn't cheat in any way, shape, or form. We just, you can see the health, a human can see the health, so we read the health, right? Just a different way to get access to it. And not always, but in general, the larger the observation space you have, the more training that will be required. And that is important because training costs money and time. So the next critical piece is the action. And actions are the abstraction of what you can do to change the state, right? You send an action to an environment, and the environment will create a new observation of the state after that action has occurred. Practically, for us, that's when you press a button on a controller. An action is a button press on a controller, and that changes the game, right? You jump, you kick, etc., right? Thus, our actions are button presses. And the action space for Street Fighter is interesting. It's not actually all of the possible combinations of buttons on an SNES controller, right? But rather all the possible valid combinations of buttons. E.g., you can't press left and right at the same time. The emulators let you, but we can't. And then we had to simplify this action space a little bit too, because like the observation space, the more actions you have available to you, the longer the training time will take. Right, and here's an example on the bottom of sort of how we defined our action space. And a multi-discrete, for those who want to know, it says like you can do just one of these and just one of those, right? And so you can press up and A or up and nothing, but you can't do up A and B. Fine, after the action, you change your observation. You get a reward for that action. And reward is what the agent will try to maximize. In our case, we spent a lot of time refining the reward and what it meant to be rewarded. Rewards are sort of where the actual interesting part of ML is. So here's some code, and again, reading it is not that important, but just to tell you that the code for the various reward functions we tried is not much code, and a lot of it is actually a lot like what a human would think about. It's like, did I win the game? Like, you know, naively you're playing Street Fighter against like your little sister, and they're mashing buttons and beating you, and you're sad, and you're like, I want to win, right? So you optimize for winning the game. Or maybe, you know, in this case, we wanted to optimize for maybe trying the net health change, or, you know, the health difference, right? Like, these are different things that you might think about. And often you want a short-term reward because it's per observation, not per game, but you want to maximize this like long-term goal of winning the game, right? And we tried a number of these. And what we ended up settling on after a lot of work is simply the delta of health between the player and their opponent at each frame, right? We wanted to reward the agent for keeping that gap high. And so here's a plot of reward over episode. And episode in this case is a game. There's 3,000 games on this plot, right? And so you can see that speed of training matters. In fact, one of the reasons we didn't use just win-loss, the binary win-loss as a reward function, is that it takes too long to train based on that reward. Finally, there are two functions in the gym environment, step and reset. And we use these to control the emulator. One, step means kind of move forward to the next frame, and that's where you send all your commands to the emulator, right? And then reset is how you reload the save state. And so these functions can from the AI world to the emulator's world, right? And Jonathan's actually going to go into some detail about the AI.
All right, so I'm going to talk a little bit about the agent side of things. So we have an environment thanks to Jim, and now we need an agent to maximize the reward from that environment. So another way is we want agents to take in these observations as input and output actions that it believes are optimal. So for this, we use a package called keras-rl. Let's just talk about keras-rl in the abstract briefly. Keras-rl provides a simple framework for making agents. The code that I'm showing on the right here is essentially a random agent. Again, you don't have to look at the exact specifics, but it's super nice interface. So what I'm showing here is something that behaves randomly. That's kind of like the base agent you would ever have, and random is actually a really good test case. Lets you make sure that all the pipeline is running and that you can perform better than random. And so Keras gives you a set of pre-built agents, a base class, training, testing, logging, plotting, maybe, all those types of things. And the two functions that we really care about in this abstraction is the forward function. So this says, like, if I give you an action, or return an action given an observation, right? So the agent is essentially reading the observation space and does a forward, and then the forward produces an action that it should be sent to the emulator to do. And then the second thing is the backward function. The backward essentially says, hey, what reward did I just get for taking that action? And then how should I change my understanding of the world and update my model so that I can do a better job next time? So the environment from Jim works with Keras in the following way. Essentially, you create the Street Fighter environment, right? This is what we use Jim to create. And then you just create the random agent and then pass in the environment. And then the most important line here is the agent.fit line. This is effectively kicks off the main loop where the agent is taking observations and sending actions and then learning and getting better over time. So we actually ended up using the DQN agent in the keras-rl library. And so we've talked pretty extensively about the environment. I'm going to briefly go into what DQN is, DQ agent, just so you're going to get a sense for that. Essentially, I'm going to go into the details of what is happening inside agent.fit. I'm less funnier. I'm not as funny as you. It's just not even, okay, anyhow. Before we start talking about deep Q-learning, let's start out with what Q-learning is. The caveat here is that in this discussion, I'm going to be focusing on the intuition, and so there's a lot of bookkeeping and math that I'm going to leave out. So let's drop this complex figure and stay at the intuitive level. So I'm going to describe Q-learning essentially by way of an example. This is a 5x5 grid. Let's say it represents a game of going from room to room. Each edge here is a doorway to another room. And when I'm in one room, I have a set of actions between 1 and 4, or 2 and 4 actions that allow me to go to another room. So suppose you enter a room and then you find cash in that room, and that's your reward. So if we map it all back, right, in the reinforcement learning paradigm Adam talked about, the location on the grid is my observation, the XY coordinate. Moving from one room to an adjacent room, essentially opening the door is your action, and then the cache is your reward. So the arrows here then represent essentially a path of actions taken and rewards received for that action. And the key thing that Q-learning does, essentially the Q-learning part before we talk about the deep part, is that it keeps a lookup table of essentially, given every state that I'm in and every action that I took, what was the reward that I received? So then when I get back to that same state later, or the same observation later, I can go to the lookup table, pull out the answer, and say like, oh, I'm going to take this one because that will give me the most reward. So that kind of maps to the 3 lines of code that I put down here. Is essentially, I select my best action. R is this lookup table I'm talking about. I send that action to the environment. The environment turns a new reward, and the most important component is then I update that lookup table with the state and the action with the new reward value. So sometimes the reward value changes over time, and so you want to keep that knowledge in this lookup table. So the big takeaway is that to complete that entire lookup table, I have to explore the entire space, not just this one path, but every possible path through the whole thing. And so that's essentially brute force. We have to explore all possible actions and all possible states. And so that's a problem. Brute force is bad generally, although, I mean, whatever gets the job done. But Q-learning is basically brute force. And so it's great if we have an infinite amount of time or if we have tiny problems, but that's usually not the case. And that's definitely not the case here in Street Fighter. Instead of having just 25 states, we have 10 to the 25 states and 24 actions. It's essentially you just multiply all the possible states in that huge dick that Adam showed earlier. And so it's effectively infinite. So brute force is too costly to do this. So deep learning essentially, yeah, I'd say deep learning allows us to overcome that huge state space. So the twist that deep Q learning lets you do is that instead of trying all possible actions and figuring out the reward for each action, we try and predict the reward even if we haven't seen it. And we do that prediction using a neural network. So for example, say I decided to go on this path starting in the lower right and just go straight up. I might predict that going straight up yields a reward of 2. That might not actually be the case, but I can predict that without having to actually do it. And so another way to think about it is that, again, at the intuitive level, the neural network is interpolating and extrapolating using simple math rather than just being a lookup table. So that's essentially what happens. We replace the lookup table with a neural network, and the neural network gives back actions that should be taken and then learns over time based on what actually happens. So in this case, if I went up and I got a 0, then I'd tell the neural network, hey, I got a 0, you should do a better job interpolating, extrapolating. So that's a brief digression into the deep Q learning approach and how the agent works. The last key part of the architecture is the controller. So this is a thing that translates actions to the environment, to actual commands that the game emulator runs, and Adam's going to talk about that.
Thanks, Jonathan. Great. So first of all, look, how great is the Python 3 standard library? Like, come on, it's really great, right? Like, we had to come up with a system for communicating back and forth between this emulator, and what we just found was like, okay, we'll just use TCP socket server, and that just worked. And then we're like, okay, well, we need some state management and some thread management, and the threading module, that just worked. And then the primitives inside the threading module for signaling between threads also just worked, right? This is great. So you're not meant to read this code, but it's more a sense of how much code we actually had to write just to communicate back and forth, and it's not very much. and it contains the entirety of our protocol between the emulator and our AI, right? And we just sent JSON back and forth between the emulator. I mean, it's really nice, right? And that's one of the beautiful things about Python. This was super fast to do. And then so where did the command go, right? So we sent these JSON commands somewhere. We sent them to a thing called BizHawk, and that's what controlled the emulator, right? And BizHawk, we had to add support for TCP sockets to BizHawk. It didn't have that. And then we had to write the code needed to read from StreetFighter memory. We needed to write the code to push the buttons we got from JSON that the Python sent over. Also, we had to learn C#, which we didn't know before we did this. I gotta say, C#, pretty nice language. I was surprised at how easy this was all to do, and I have to thank the BizHawk developers for the just general cleanliness and organization of their code. We have open sourced the code we used in here. I just don't go read it unless you're gonna make a pull request. We did it fast. And so the limitations of the emulator code actually meant that we had to try a bunch of techniques before settling on the socket code we just showed you. So BizHawk actually contains a Lua interpreter in it, which is great. But the Lua interpreter they have doesn't support network I/O. It does support file I/O and SQLite, so we did try to shove all this together via like writing to a file, reading from a file, or writing to a database row, reading from it. That's a terrible idea, don't do that. It was also very slow. We were able to run the emulator basically at 60 frames a second using file I/O, 120 using SQLite, and then finally when we switched to Python socket server, we got 450 frames per second while we could run we could do three games training at a time on a Windows machine in Google Cloud. This actually saved us a ton of money, so because we're training in the cloud, right, that's money and time. Performance is a huge feature, right, and Python was able to get us significant performance gains. Now, great, we have 450 frames per second. We have a fast performing system. We had a good architecture. But now we actually have to train. Like we have to do that part of AI where you teach it things. Here's a tiny snippet, and I cannot emphasize the tininess of it, of the results of the actual training. We spent hundreds of cloud compute hours and human hours tweaking all of these parameters. It's just like a matrix of all the parameters we messed with. And to figure out what works well, like deep learning is great, but it is also sometimes alchemy, right, which is unfortunate. And we tried to, we tweaked the neural network parameters, we tweaked the environment, we tweaked the number of games, tweaked feature representation, training parameters, et cetera, et cetera. We tried to be relatively scientific about it, changing one thing at a time. But in the end, we were wrong about pretty much every assumption we made to start, right? It's fine, this is how it goes. But we did build a system that let us iterate incredibly fast on being wrong, and that actually was a really helpful thing to have done. So about 3 days before the conference, to our relief, we finally got an agent trained that did well. And you'll see on the screen, if the video loads, we get to watch some awesome Street Fighter stuff. So this is after 3,000 games. We have an 80% win rate. The AI is on the left. It's Dalsim. And what you'll see here is some interesting stuff. Dodging, blocking, special moves, backing away, avoiding damage, winning the game with a fireball. It's pretty dope, right? It's pretty cool. We were very excited when that happened. And now here's our non-boring booth with all of our homemade signs. Look, we were a startup, right? The laptop actually that you see here is actually training agents. The display is showing the training of 4 agents at a time so people can watch it happen. And the way we initially trained our agents actually against the Super Nintendo CPU and 3-star difficulty. And then later we trained them against each other. At the conference, we ran a Final Four style tournament, like I said, to see which bots we trained was best. We had a competition inside this. If you guessed which agent was going to win, you could win a Super Nintendo Classic. For those Super Street Fighter fans out there, you'll notice that M. Bison is not on this bracket. That's because he's OP. He's totally overpowered, right? And our AI figured this out really fast. It was like right away. And then we watched the first tournament. We're like, oh, this is just not good. It was just a clear sweep. And so we banned him from the second tournament we ran due to performance-enhancing drugs, AKA his code. So the second tournament we ran actually ended up going to Saget. And if you want to know who the best character to play is, well, if you are an AI, it's M. Bison. I don't know if you're a human. I'm terrible at this game. And I have to say, for those of you who might have to do this sort of thing in the future, people loved this idea, right? They loved watching all these matches. This little kid over on the right-hand kind with his hand over his heart, he was like crying when his character lost in the tournament. We were so sad, but he loved every minute of it. He would just come and watch the booth when we weren't even having the tournament just to see the characters fighting. We had about 80 people just kind of screaming and yelling during the whole tournament. I mean, it's a great way to do it. And so much better than a t-shirt and like a video of our software. There's a lot to love about Python and artificial intelligence and machine learning. I mean, there's a lot to love about Python in general. We know the iteration speed, the batteries included nature of it, right? The standard library, good abstractions. Like, we're all here for that reason. But Keras, Gym, TensorFlow, SciPy, these are world-class tools that are easy to use, they're free, they're community supported. It's amazing, right? It's great. And it's actually not just Python that we love, it's programming in general. And one thing I in particular love about programming is sometimes I make really hilarious mistakes, right? So this is a chart of our AI's win rate playing against a literally motionless opponent, right? So we start out really strong, like we win a bunch of the first couple hundred games. But then how do we lose? I don't even know how we ended up losing. I think we just ran into the opponent and we died over and over again, right? But actually it's a great outcome, right? It's scientific, it's an important one, and we learned from it. And it was pretty funny, and we all learn sort of from funny failures like this. And so like, I want to help new and experienced programmers understand that it's okay and normal to make mistakes like this. So I'm asking you guys, some of the experienced people or the new people, to tweet out your funniest programming fails, right? Like with hashtag PyCon 2018 and then hashtag reward function. This is my joke on us giving you a prize for this. So, and by the end of the weekend, like the person with the most retweets, we'll track you down and send you a Super Nintendo Classic, because I think that'd be pretty fun. You can tweet, we're at BlueVoyant, but just tweet about it and tell us about the times you've made mistakes. Make sure they're yours, not someone else's. Make sure they're educational and funny, right? Because we want to teach people it's fine. Like, yeah, you're going to screw it up. And that's the best part about programming. It's completely safe, and you get to learn that way. So thank you. If you have any questions, we hope our story was interesting. In fact, we have another one. So the company we were talking about, Gyroscope, we got acquired by an amazing security firm called BlueVoyant. I would be remiss to say we are hiring if I didn't say that. Come talk to us about this. Come talk to us, ask us questions right during this talk. And then we're around all weekend. You can come find us at lunch tomorrow if you want to talk about AI in general. And yeah, thank you very much. We're happy to take questions.
Thank you so much, guys. We got a few minutes for questions, so please come to the microphone if you've got one. There's one front and center here. I would ask you use this time only for questions directed at the speakers. If you want to talk about anything longer, have specific add-on comments, feel free to catch them in the hall after the talk. Thank you.
Hey, quick question. When you guys made all this, did you guys account for, like, say, peak human performance and peak human reactions? Like, in a 60 FPS game, I understand it to be like a 15 frame delay between an action and someone being able to react to that.
Great question, and the answer is yes, we did. So the AI actually only acts every 20 frames because actually for a number of reasons. One is that the training would have taken too long if we acted every frame. So that's this important, but also against humans, it's pretty much only fair to do that. This would just, I think over time, if we just trained this, it would just destroy every human. Like it wouldn't even be close. If we enabled like every frame. That's a good question.
So, so the question I had was about like a time delayed attack. You know, so if Ryu like throws a fireball from the other side of the screen, and then coincidentally ducks, you know, when it hits the opponent, if you're only just considering that one frame, could your AI not learn that, you know, ducking equals damage to the opponent?
So essentially the rewards and the failures are propagated back. So it's kind of like an exponential curve. But yeah, it will eventually figure out that like this observation that it made like 10 frames in the future will then like suffer the actual consequence.
Okay. Thanks.
Yep.
Hi. Do they learn special moves on their own, or did you intentionally do anything with them?
They learn special moves on their own. So they just have the key presses, right? And they have every 20 frames they can insert like a key press pair, essentially one joypad and one button. And so they actually like that move that I shot at the end just started with like key presses, and he figured out how to shoot the fireball.
Thank you.
Hey, two quick questions. Have you considered hurt boxes or hit boxes in the machine learning?
No.
Okay. And then second, have you considered challenging any professional players with your bot?
Yes. Let me answer that question. So we were able to know the X and Y coordinate of every player. And so that was like a way for them to figure out how close they were to each other and when they should be doing moves or not. And I think they also knew who their opponent was. So they're kind of indirectly learning where the hitbox is. And then we've actually talked to one of the top 5 players. After we did this and had a fun blog post, he wanted to compete against it. So we need to set up a tournament.
Was it
and do
Daigo?
it. There's actually a whole nother funny story about potentially doing a marketing campaign for L'Oreal by making an AI bot. Anyhow, again, come talk to us. Okay. Yeah, come talk to us.
That doesn't do anything for me.
How much did the training cost? Like, could I do it on my own computer?
Yeah, sure. So actually, we did a bunch of it on our own computer with a. We initially didn't even do it with GPU optimized. We just did it on like a local Windows machine, it was a fairly powerful gaming machine, but we actually didn't even use the GPU. In the end, we did use Google Cloud Compute so that we could have lots of computers going to train all of the agents all in parallel. But you could do the training on your own computer, and it wouldn't cost you that much. We really just paid so that we could do it in parallel. You know, if we had like 40 Windows machines at home, we would have done it that way too.
And how much did the cloud cost?
I mean, I think we used the free subscription.
Oh.
So there's the first 720 hours free or whatever. Yeah. And then Adam used to work at Google, so maybe we got a little extra. But essentially each game took about 3 hours to train at 450 frames per second, and then you could train essentially 3 or 4 games in parallel on the same computer. So it wasn't too bad.
I'd like to ask about sort of what your guys' backgrounds are, like your academic backgrounds, because I've noticed that a lot of machine learning and AI jobs seem to require PhDs.
Okay, so I'll answer it first. And I will answer it for him too. So my background is I actually have a business degree, but I was a site reliability engineer at Google for many years and ran very large-scale systems, and I'm a software engineer for a long, long time. So and still do some of those things when I'm not in meetings. However, Jonathan Mortensen over here is better known as Dr. Jonathan Mortensen, and he has a PhD from Stanford. He never talks about it, but you should, when you see him tomorrow or ask him questions, address him as Doctor. He really likes that.
I don't think that you need PhD. To be clear, my PhD was like in biomedicine, doing like, EHR analysis. So like, you don't need it. Just to be clear, I don't think that there's any gate there.
One interesting thing that happened to us, we got an email from some students in Pakistan who used our code to do this as one of their undergraduate projects. They just kind of redid our work. And they, they don't have PhDs, but they were able to figure out different techniques and different reward functions and things like that.
Cool, thank you.
Hi there. So one of the things that's been taking the retro gaming community by storm is randomized games. So things like Super Mario Bros. 3 randomizer, Link to the Past randomizer. So what I'm wondering is how might AI adapt to games where some of the underlying parts of it is randomized, but the rules remain the same?
I think it's really a question about how well characterized the observations are, and so what can happen when you're doing machine learning, right? Is like you kind of learn, you overfit, right? You kind of learn exactly how the game plays. Like even if you know the rule set, you're like, oh, I saw this frame, and I know that if I see this frame, I just have to do this thing next, instead of actually interpreting what's going on in the frame. But I think if you have a good representation of that state space, I think it should, as long as the rules are consistent, it should learn.
Thank you.
I have a question about how you chose the hyperparameters. You showed us that spreadsheet, and it sounded like there was a lot of hand tuning to kind of get the magic combination. Just generally, what are your thoughts on I guess, algorithmic or more automated ways of finding hyperparameters, whether it's genetic algorithms or something else? And generally speaking, when do you feel those types of methods are going to be successful versus when you kind of have to tweak numbers by hand?
That's a complicated question. I think, yes, you want to use some heuristics to do essentially a grid search. Oftentimes you can't do a full brute force grid search, but using some heuristics which say, oh, if I make this tweak, the performance goes up. I mean, essentially it's not really, maybe sometimes parameter optimization is a convex problem, but it's usually not, so you gotta kind of explore the space. Hand tuning, there's still a place for that, and there was a place here, which was that, one of the things that we were tuning was frame skip, and that required some intuition about how you play the game and making sure that that lines up all together. So, I mean, I think that machine learning isn't a silver bullet. You still need to understand the domain that you're trying to model and behave in, and so there's a place for both. But using grid search is almost great as well. I mean, if you can do things in compute that's cheaper than like your time, then you should do it that way. And if you can also add some of your intuitions, you should too. It's kind of a non-answer answer.
How are we doing?
Yes, thank you. That's all the time we have for questions now. If you'd like to meet with the speakers in the hall afterwards, feel free to do so.
Thank you very much, everyone. Appreciate it.